Hello, welcome to module 3 of lecture 5. In this module, we will look at the next heuristic time constraint scheduling strategy known as force directed scheduling. Now, force directed scheduling, the goal is to reduce hardware by balancing concurrency. So, what do we mean by concurrency here? The number of operations that I have to concurrently schedule at a given time step. So, if we can balance the concurrency, distribute the concurrency into different time steps as evenly as possible, we will maximize the usage of resources over these time steps, and hence it will lead to a minimum resource scheduling within a given time bound. So, it is an iterative algorithm. One operation is scheduled per iteration. After the iteration, the information that is the current on the current speed and area that has been obtained is fed back to the scheduler, and the subsequent scheduling decisions are dependent on this information. So, how does this strategy proceed? So, we will first look at the scheduling strategy, overall scheduling strategy here, and then see the different components and explain these different components. So, repeat until all operations have been scheduled. As we said, in each step we will have one operation scheduled. So, the step operation is to evaluate time frames. We will look at what time frames are, and to evaluate time frames we will require the ASAP and ALAP schedule of the operations at that time step. Then we update distribution graphs. So, we will understand what distribution graphs are. Then we will calculate self forces for every feasible control step. Then we will calculate predecessor and successor forces. After calculating the self forces, predecessor forces and successor forces, we will find out the total force, and we will schedule the operation with the least force. That means this corresponds to highest stability that we will see. So, the operation whichever operation is now selected by after step 5 is the time step at which the operation should be scheduled. So, as we said, we have to first determine time frames, and in that time frame the first work for us was to determine the ASAP and ALAP schedule. The initial ASAP and ALAP schedule is obviously the ASAP and ALAP schedule that we have been considering in all the classes till now. The left one produces the ASAP schedule, as soon as possible schedule, and the right one gives me the ALAP schedule, as late as possible schedule. So, based on that we obtain the time frame for each operation. We will determine the time frame for each operation. And what is the time frame for an operation? The time frame for an operation is equal to its mobility plus 1. How is the mobility obtained? Mobility is given by the ALAP time minus the ASAP time, and that is why we found the ASAP and ALAP schedules. Now, given the time frames, we have these boxes where the length of a box, that means this is the length of a box, the length of a box is equal to its possible execution cycles. For example, the length of this is operation 1 V1, V1 has a length of 1 because it has to be scheduled. If I have a latency bound of 4, then operation 1 must be scheduled only, it must start at time step 1 only. Similarly, operation 2 must start in time step 1. Operation 3 must start in time step 2. Operation 4 must start in time step 3, and operation 5 must start in time step 4. Why? Because these are all the operations in the critical path. Now, let us take operation 6. Operation 6 has a length of 2 time steps. Why? Because it is possible to schedule it in either time step 1 or time step 2. So, here we see that the time step is 2 because the mobility of this operation is 1. For all the operations in the critical path, the mobility of these operations are 0, and hence the time frame is 1. Here the length is 2 because the mobility is 1, length means the time frame is 2 because the mobility is 1. That means operation 6 can either be scheduled in time step 1 or time step 2. Similarly, operation 7 can either be scheduled in time step 2 or time step 3, and rest for the others similarly. Operation say operation 8 can be scheduled in time step 1 or time step 2 or time step 3, its mobility is 2 and its time frame is therefore 3, and these are the possible time steps. 1, 2 and 3 are the different possible time steps in which 8 can be scheduled. What is the width of a box? The width of a box is its probability of assignment, okay, and is given by 1 by the box length. So, if the box length is 1, that means the probability of assignment is 1. That means that operation must be scheduled in that time step. Okay. So, that is why the width of these operations are 1. The width of the multiplication operation V6 is half because its box length is 2. So, 1 by time frame. So, 1 by time frame is the probability of the operation. So, the probability of the operation is 1 by box length within its time frame and 0 outside it. So, the probability of assignment is 0 outside the box and is equals to 1 by time frame within the box. Now, uniform probability distribution is there within the box, which goes to say that the area assignment equals to 1. That means that all operations have take the same area. So, that is why we have shown here that the area of each operation is 1. This is a measure of the total area of the box is the measure of the area that this operation will take on the floor of the chip. So, then we said that after we have calculated the time steps of the operations, the next work is to create distribution graphs. What is a distribution graph? The distribution graph is the sum of the probabilities of each operation type for each control step in the data flow graph. So, it indicates the concurrency of similar operations. For example, let us see for the multiplication operation. For the multiplication operation, it says that that at the first time step, the value of the distribution type for the distribution type multiplication, the value is 2.8. So, how does this 2.8 come? It is 1 plus 1 plus half plus 1/3. So, the different, so what is it being summed upon? It is the sum of the probabilities of all operations that of all operations of a given type that are possible to schedule at a given time step. That means, at time step 1 of type multiplication, there are 4 possible operations that can be scheduled in time step 1, and the sum of their probabilities are 1 plus 1 plus half plus 1/3, and that is around 2.8. For the second time step, what do we have? We have 1 plus half plus 1/3. So, 2.33 is the DG value, is the distribution value for the multiplication operator at time step 2. Now, what does this sum of these probabilities indicate? It indicates the pressure on a resource due to the concurrency of operations. Hence, the pressure of concurrency, that means the number of operations that I need, that I may be forced to schedule in time step 1 is high, and hence this value of the summation of probabilities is high. So, it indicates the concurrency of similar operations at a time step. So, similarly, we have these values for the addition, subtraction and multiplication operations. So, what does the distribution graphs show? The distribution graphs show the likelihood that a resource is used at a given C step. Now, we will understand the concept of forces. So, first we understood the concept of time frames, which is 1 plus the mobility, and we also understood the concept of the probability of assignment of an operation at a given time step, which is 1 divided by the time frame of that operation. And then we understood distribution graphs. We said that the distribution value of a distribution graph for a given operator at a given time step is equal to the summation of the probabilities of that operation type at that time step. So, and that indicates the level of concurrency of that operation type at that time step. Okay. Forces determine the selection of a candidate operation for a C step. Now, depending, we will have a concept of forces, and that will determine which candidate, that will prioritize the operation to a given time step. The forces of different operations will attract or repel each other, and finally, a certain operation will be scheduled at a given time step, so that the stability of the system is maximized. What we mean by that and how we get it, I am just coming to. So, assignment of an operation to a C step changes the probability of assignment. Probability becomes 1 in that C step and 0 in other C steps. So, when we actually assign an operation to a C step, the probability becomes 1 in that C step and 0 in other C steps, other control steps. So, let us say that I could schedule an operation in 2 time steps. So, its probability of assignment was half in the first time step and half in the second time step, and then we have forced that operation to be scheduled in the first time step. So, the probability now becomes 1 in the first time step and 0 in the second time step. Now, how does this forces relate to these probabilities? Now, the variation in probability has been equated to the displacement of a spring in Hooke's law. So, Hooke's law tells that the force on a spring is proportional to the displacement x. The force F on a spring is proportional to the displacement of the spring, and that displacement value is given by x. Here, the probability of assignment, the variation in the probability of assignment has been equated to the displacement of the spring. The value of type distribution at that C step, the value of the type distribution at that C step, that is the DG value, the distribution value has been equated to be analogous to the elastic constant K. Now, larger the force, larger is the concurrency. So, what do we try to do? We will explain this with an example subsequently. So, what do we do? The objective is to obtain a latency bounded schedule with low overall concurrency for each resource type. Why? Because this ensures high resource utilization. Now, we come to the concept of self forces. So, basically forces are of 2 types. Self force, which tells me what? It tells me the set of forces relating to an operation to the different possible C steps where it can be scheduled. Every operation has a self force for every C step of its time frame. There are also, along with the self forces, there are predecessor successor forces, and that is related to operation dependencies. So, how do we compute the force of operation I for a given type of resource? It is given by the distribution graph for resource K multiplied by the change in the operations probability. So, DGIK, what does it tell me? It tells me the current value of the distribution graph for resource type K, and Xi is the change in the operations probability. Now, the total self force associated for assigning an operation at C step j is given by summation over all its possible time steps where it can be scheduled, and what do we sum up? We sum up the force. So, self force at time step j is given by the total force for that operation at different time steps where it can be scheduled. Now, we come to the example. So, what is the self force corresponding to operation 6 in C step 1? We said that operation 6 can either be scheduled in time step or C step 1 or in C step 2. In C step 1 it has a probability of 0.5, in C step 2 it has a probability of 0.5. Now, how do we calculate self forces? We said that the self force is the summation of the forces at time step 1 and 2 for operation V6. So, what is the force at the first time step? The dg value for operation 6 at the first time step multiplied by its change in probability. What is the change in probability? The change in probability, we said that previously it was 0.5 and now it has changed to 1. So, the change in probability is 1 minus 0.5, which is plus 0.5. And what is dg corresponding to that? We said that dg corresponding to the first time step was, for the multiplication operator, was 2.8. So, dg1 was 2.833 multiplied by the change in probability of operation V6, which is 1 minus 0.5 plus the dg value at operation for the multiplication operation at time step 2. The dg value for the multiplication operation at time step 2 is given by this one. So, it is 2.3. So, dg2 is 2.33 and x2 is minus 0.5. Why? Because I have not scheduled that operation here, my probability is 0 now. What was my probability previously? It was 0.5. So, 0 minus 0.5 gives me minus 0.5. So, the total self force for scheduling operation V6 at time step 1 becomes 2.833, which is the distribution value from the distribution graph of the multiplication operation at time step 1 into plus multiplied by plus 0.5, which is the change in probability of operation V6 if it is scheduled at time step 1, plus the distribution value for the multiplication operation at time step 2 multiplied by the change in probability for not scheduling the multiplication operation at time step 2, which is minus 0.5, and therefore, the total self force at the first time step becomes plus 0.25. The self force for assigning operation V6 at C step 2. What is that? We found out the self force for assigning operation 6 in C step 1, and now what is the self force, total self force for assigning operation 6 in C step 2? The total self force is given by, again, dg of 1 into x1 plus dg of 2 into x2. So, now what does this give me? Here the dg remains same, 2.833. However, now I have not scheduled the operation V6 in time step 1. So, previously my operation probability, assignment probability was 0.5, now it is 0. So, 0 minus 0.5 gives me minus 0.5 plus the dg at time step 2, which is 2.333 multiplied by plus 0.5, which is why? Because now it becomes 1 minus 0.0.5, the 1 minus plus 0.5, that is the change in its probability of assignment, and this value is minus 0.25. So, we find that the self force corresponding to operation 6 is lower in time step 2 than in time step 1. After we have found out the total self force for the operation, we have to find out the predecessor successor forces. Now, what are these? Scheduling an operation may affect the time frames of other linked operations, right. So, when I have fixed, let us say operation V6 in time step 2, let us say, then I am forced to schedule operation V7, which is the linked operation here at time step 3, right, must be scheduled at time step 3, and hence the linked operation, the time frames of the linked operations now change. Now, due to this, this may negate the benefits of the desired assignment. So, if we consider only self forces, we could do the scheduling based only on self forces. So, what would that do? It would find the self force of each candidate operation, each ready to schedule operation at a given time, and then it would take the least self force, the one with the least self force, and schedule it. However, if we consider only self forces, I am not considering the effect of the operations that this schedule, that this assignment of my current operation has affected on other linked operations, and that may negate the benefit of the assignment of this operation at the current time step. So, predecessor successor forces is the sum of the self forces of any implicitly scheduled operations. So, what does this tell me here? Now, assignment of operation V6 to C step 2 implies the assignment of operation V7 to C step 3, as I was saying. Now, what is the self force of V7 when it is scheduled on C step 3? Right. So, that will be this, the dg2 into x2, because I have not scheduled, it is possible to schedule operation V7 at time step 2 and time step 3, but I have not scheduled this operation in time step 2 because my times my time frames have reduced, and I have actually scheduled it on time step 3. If I do that, then dg2 is 2.333 multiplied by x2, which is minus 0.5. So, 2.333 into minus 0.5 plus 0.833 into plus 0.5. So, minus 0.5, because the probability of V7 at time step 2 was half, and I have not scheduled it on time step 2. So, the change in probability becomes 0 minus 0.5. So, it is minus 0.5, the change in probability, and for time step 3 the DG value, that means the concurrency value, is 0.833. Let us just look back and see why is that so. This is because in time step 3 I can only schedule either V7 or V8 in time step 3, and the probability of V7 is half and the probability of V8 is 1/3. So, 1/3 plus half is the total distribution value at time step 3, and that is equals to 0.833. So, the total successor force, is minus 0.75. Why? Because the successor force is now given by the scheduling of operation V7 at time step 3. So, the total force for scheduling the operation V6 at time step 2 is self force of V6 at time step 2, which was minus 0.25, which was minus 0.25 here, and plus the successor force which it induces on time V7, which is minus 0.75. So, the total force becomes minus 1. Now, likewise for all operations, I will at each step for all operations I will calculate the total force, I will find out the minimum force, and I will schedule that operation with the minimum force at each time step, and that until all operations have been scheduled. Now, if we go back to the algorithm, we should understand it better now. So, what are we doing? So, repeat until all operations are scheduled, evaluate time frames, find the ASAP schedule, find the elapse schedule. So, based on the ASAP and elapse schedule, now you find time frames. Now, the time frames is equal to the mobility plus 1, find out probability of assignment, which is 1 divided by the time frame value. Now, given the probability of assignments, find out the distribution graph for each operation type, and that distribution graph for each operation for a given operation type will give the distribution value for that operation type at each time step. Then calculate self forces for every feasible control step. Then add the predecessor and successor forces to the self forces, and then find the total force, find the operation with the least total force and schedule that operation with the least force. Set the time step of that operation to the selected C step. So, if I schedule operation V6 in time step 2, because let us say assume that the total force total force with respect to V6 at time step 2 is lowest, then the start time of V6 will be assigned equal to 2. With this, we come to the end of module 3 of lecture 5.